Autant más.
Eu acho que é 50 minutos. Puedes extender a tu mano.
Eu sinto muito. Eu sinto muito. Tu peux faire un double écran.
Well, I have the pleasure to present Professor Etienne Ghys from the École Normale Supérieure de Lyon that will talk about commutators and diffeomorphisms of surfaces for us today. Professor Etienne Ghys is closely related to IMPA since the first time that he came here, 1978, perhaps 1979, as a coopérant du service militaire de France. And since then, he has been closely related to IMPA and also to other Brazilian institutions, and has become an important point of reference for us in France. So, with us, Professor Ghys.
Thank you, Cesar. So indeed, this is a great pleasure for me to be here. So as Cesar was reminding, I came here at a very early stage of my career. Actually, I came here the day following my PhD defense. So I really consider myself as being a student of IMPA. So I would like to thank IMPA for everything, for its wonderful hospitality, for the library, and above all, for all the people here. So thank you very much for everybody. So today, I want to discuss a topic which is kind of a mixture of elementary algebra, some geometry, and some dynamical systems. I will try to be as elementary as possible, and I will not go into the technical difficulties. So let me begin by some very, very elementary algebra and start with a very general group. So you start with a group, any group for the moment, gamma, and let me recall that a basic tool when you want to measure if a group is commutative or not is to compute the so-called commutators. So if you have two elements, A and B, in a group, the commutator of A and B is, by definition, the element A, B, A inverse, B inverse. One has to take in mind the fact that the set of commutators in a group is not a subgroup, just a set in general. So if one wants to make a group out of this set, the only possibility is to consider the so-called first commutator group or first derived group, which is the group generated by commutators. And so, even in this full generality, we arrive at some algebraic interesting problem, which essentially has not been studied deeply up to now, which is, given an element of this subgroup gamma prime, one could ask how many commutators do you need to write it as a product of commutators. So this group gamma prime, by definition, an element is this, an element in gamma prime is a product of commutators, so you can try to minimize this number of commutators. And this gives you a very interesting number that I will call the commutator length of the element gamma as the minimum number of commutators. So in this full generality, of course, you cannot say anything. And before I go further, let me give some examples of groups that I have in mind, which essentially come from, let's say, dynamical systems or something like that. Let me mention first a few results. First, an old result of Michel Herman. He proved, a long time ago, that if you consider the group of all orientation preserving, say, infinity diffeomorphisms of the circle, this group has the property that any element in this group can be written as a product of two commutators. 1 in general is not enough, but 2 is always enough. That's a non-trivial theorem. A slightly easier theorem, due to John Mather, is essentially the same, but in the context of homeomorphisms of Rn with compact support. John Mather proved that any homeomorphism of Rn with compact support can be written as one commutator. This is not so difficult. And putting all these things together, so I've put here a few names, Smale, Herman, Thurston, Mather. So I think this was conjectured by Smale, maybe, I don't know, is it true or not, I don't know. If you consider any manifold, let's say connected manifold, M, and if you consider the group of CR diffeomorphisms of M with compact support, and if you consider the connected component of the identity of this group, that I denoted by diff 0 for connected component R for differentiability R of M, this group is a simple group, meaning that there is no normal, non-trivial subgroup in it, and in particular, it is equal to its first commutator group. So any diffeomorphism isotopic to the identity of any compact manifold can be written as a product of some commutators. How many? We don't know. And this is basically the kind of questions I would like to discuss today. How many commutators do you need to write a diffeomorphism as a product of commutators? In the full generality, it seems to me that this question is completely open. So I will describe some cases and ask a few questions. Before I go into these very complicated and huge groups like diffeomorphisms, let me go to some more elementary group, and maybe the most simple one, the most elementary one, the free group on two generators. So here is a typical question. Consider the free group on two generators A and B, and choose as an element the commutator AB raised to the nth power. So by definition, this is a product of n commutators, because it's the power of a single commutator. Question: is it possible to write the single commutator to the nth power in a shorter way? Can you write this product of n commutators with less than n commutators? That's the question. So when I saw that, this is a question of somebody called Neumann from algebra. And when I saw that, I say, it must be true. How could you guess a shorter way of writing commutator AB to the nth power as being a product of less commutators? And this is not true. This is not true. And let me show you a formula that I like very much, which is due to Köhler and to my former colleague Bavard. This is an incredible formula. Here's an identity. The cube power of a single commutator can be written as a product of two commutators. If you expand the right-hand side, I promise you get the left-hand side. And the incredible thing is that my colleague Bavard, he found that just by playing with formulas, you know, some people like that you know, they're playing with formulas, and he got that. And later on, it looked like incredible, and he understood it using topology. I won't explain that today, but he understood it, so to say. It is not miracle. And then he proved that actually, if you take the single commutator AB to the nth power, it is possible to write it as a product of much less commutators than n. N over 2 is enough. So there is a similar formula for the single commutator AB to the nth power as the product of n over 2 commutators. Actually, the formula is here. you need the integral part of n over 2 plus 1. So I will not explain to you how it's possible to write explicitly the nth power of a single commutator as the product of n over 2 commutators. But I want to explain to you the idea of why it is not possible to do better than n over 2. In this theorem, you have two parts. One is that it is possible to write single commutator AB to the nth power as the product of n over 2 commutators. This is part one. And part two, it is not possible to do better. So I will explain to you how it's possible to prove lower bounds. So to produce lower bounds, the general trick is this. I will introduce a definition which is fundamental for this talk. It is a so-called notion of quasi-homomorphism. So again, I want to stick to very general context. You have a group gamma and a map phi from gamma to R. Then one says that this is a quasi-homomorphism if it is a homomorphism up to a bounded error. So this means that there is a constant C, depending on phi, such that when you evaluate phi of gamma 1, gamma 2, minus phi of gamma 1, minus phi of gamma 2, which would be 0 if it were a homomorphism, this quantity is uniformly bounded by a constant C independent of gamma 1 and gamma 2. So this is definition of quasi-homomorphism, and of course, if the constant C is equal to 0, you get the well-known notion of homomorphism. And the idea, of course, is that if you evaluate a homomorphism on a commutator, you get 0. So if you evaluate it on a quasi-homomorphism on a commutator, you get quasi-0. So let me go into this idea. So let me try to do some computation for you. I am not good for computation, so I hope you will forgive my computations. Here is what the computation. Suppose you have a quasi-homomorphism phi. And suppose you want to evaluate it on a product of k commutators. So you have to compute phi of A1, B1, A1 inverse, B1 inverse, and so on. You have to compute that. Well, you say phi is quasi-homomorphism. So this means that phi of AB is phi of A plus phi of B plus an error, and the error is less than this constant C. So of course you can write that this big quantity, phi of A1, B1, A1 inverse, and so on, is equal to phi of A1 plus phi of B1 plus phi of A1 inverse, and so on, with an error which is equal, which is at most k, 4k minus 1 times the constant, because you have a word of length 4k, so you use 4k minus 1 multiplications. So you have this bound. Now, say phi of A1 plus phi of A1 inverse is equal to phi of identity, up to an error. So in the same way, you can say that this quantity is equal to 2k times phi of identity, up to an error, which is 4k minus 1 plus 2k, which is 6k. Now, phi of identity is less than the constant. So this quantity is equal to 0 up to 8k times the constant. Well, if you put this together, what you get finally is that if you have an element in the first commutator group gamma, and if this element can be written as a product of k commutators, then you get a lower bound for the number of commutators. This lower bound is the value of the quasi-homomorphism on gamma divided by the constant. So this is general strategy. If you give me an element in a group, and if you want to find a lower bound for the number of commutators, the trick is this. You produce a quasi-homomorphism which is as big as possible when evaluated to gamma, in order to have a numerator which is as big as possible, and with a constant C as small as possible. So you try to find a quasi-homomorphism which is a homomorphism as much as possible, and which is as big as possible on a commutator. So I will give examples. This is general strategy. So let me go to a few examples to show how this trick works. There is a so-called Brooks quasi-homomorphism. Here's the thing. Consider the free group on two generators, F, and choose a word, W, in F. For example, you could think W is AB, just a single word. Now I'm going to define a map from the free group to Z, and the map is this. You take an element, gamma, in the free group. An element in the free group is just a word in A and B. And you scan inside the word how many times you can see a subword, which is W. So you look into your long word gamma, how many times you can see W. And you deduce from that the number of times you can see W in the opposite word. This definition. And I claim that obviously this is a quasi-homomorphism. Why? Because if you have a word gamma 1 and then a word gamma 2, if you scan for W inside gamma 1, gamma 2, you will count how many times W occurs in gamma 1, then the number of times W occurs in gamma 2, but maybe you will miss the few possibilities where W overlaps between gamma 1 and gamma 2. And so if you think a little bit, this tells you that this map, phi W, is indeed a quasi-homomorphism with a constant equal to twice the length of W. Okay? So let's try to apply this kind of idea to our original problem of bounding.
What about the simplification?
Yes, that's why there is the minus sign. If you have a simplification between gamma 1 and gamma 2, this means that the certain end of gamma 1 is the exact symmetric of the beginning of gamma 2. So this means that each time you see some W in the end of gamma 1, you will see W inverse in the beginning of gamma 2, so they will collapse. Okay, I was just cheating, but not in front of you, sorry. Okay, so let's try to apply this trick to our problem, a single commutator. And let us choose the word W is AB. So what's the evaluation of phi W on this single commutator? So it's A, B, A inverse, B inverse, A, B, A inverse, B inverse, and so on. How many times do you see AB? N times. A, B, A inverse, B inverse. A, B. You see AB once in each single part. How many times do you see the inverse of AB? Never. Because the inverse of AB is B inverse A inverse. Okay? So you see 0 times W inverse in A. So when you evaluate the phi W on gamma, you get N. Now the constant corresponding to this, I told you it's twice the length of the word, it's 4. So if you apply the inequality I gave you in earlier transparency, you get that the commutator length is at least, n divided by A times 4, n over 32. So you do not get the bound I told you, n over 2, because I was not cautious in choosing the correct W, the correct word, the correct homomorphism. But believe me, if you are just a little bit more clever, you get the exact bound, n over 2. So this is general strategy. If you want to evaluate commutator length in a group, it's a good idea to try to build quasi-homomorphisms. Actually, and I will explain that quickly, this is not very important for the rest, this strategy of constructing quasi-homomorphisms is the only possible one. So let me explain what I mean by that. Again, if you have a general group gamma, you might try to stabilize the commutator length. So this is a general definition. You define the stable norm of an element gamma as being the limit when n goes to infinity of 1 over n commutator length of gamma to the nth. You say that a quasi-homomorphism is homogeneous if it satisfies phi of gamma to the n is n times phi of gamma. And there is a kind of a duality, which is also due to Bavard, which tells you that you can compute, actually, it's kind of a Hahn-Banach theorem. You can compute the stable length of an element gamma as being 1/2 of a supremum of the evaluation of phi of gamma divided by norm of phi, where norm of phi is some norm for the homogeneous quasi-homomorphism. So don't forget it. What I mean is this. If you want to find a lower bound for commutator length, there is only one way. Find the correct quasi-homomorphism. This duality here tells you that stable length and quasi-homomorphisms are dual objects. If you want to understand something concerning the first, you have to understand something concerning the second one. So I will move my ideas, and instead of trying to understanding commutator length, I will try to build as many as possible examples of quasi-homomorphisms. Before I go further, let me give another example that many people in this room know from dynamical system, which is the so-called rotation number. Everybody, or many people here know that a single homeomorphism of the circle with orientation preserving homeomorphism of the circle has a numerical invariant which has been introduced by Poincaré and which is an element of R mod Z. And this is the so-called rotation number, which is so important in dynamical systems. And this map, rho, is definitely not a homomorphism. Rotation number of a composition is not the sum of the rotation numbers. However, when you lift this map to the so-called universal cover of the homeomorphism group of the circle, you get the so-called translation number. And translation number, even though it is not a homomorphism, is a quasi-homomorphism. This is something that everybody in dynamical systems know. And what I might add, and this is an observation I made at IMPA in 81 or something, that actually one can abstractly define rotation number as being the only quasi-homomorphism on this group. The translation number is you can define it like in many books, taking limits and so on, but forget about it. Translation number is the only quasi-homomorphism defined on homeo tilde of the circle. So this gives an abstract interpretation of translation number. Okay, now let us try to go to the main part of my talk. I would love to do similar things for diffeomorphisms of higher dimensional manifolds. And this is very difficult, and I don't know how to do. So one way between dimension 1 and dimension 2, I would say, is dimension 1.5. And dimension 1.5 would be diffeomorphisms of surfaces preserving area. So I will try to tell some things about evaluation of commutator length in the group of diffeomorphisms of a compact surface, S, respecting area, which I would think as being something intermediate between circle and surfaces. So I want to describe in this talk some constructions and some understanding of commutator length. So this little 0 here means connected component of the identity. So I will try to restrict myself to diffeomorphisms of a compact orientable surface S isotopic to the identity and preserving some area form fixed once for all. And I will discuss the three possibilities. One is the surface could be a two-sphere. The surface could be the two torus, or the surface might have higher genus. So I will not follow this ordering because the first one is the most difficult one. So I will begin by the torus, T2, then I will go to the higher genus case, and at the end of the talk I will say something about the case of the sphere, S2, which is the hardest case, and this is the case that I like most, of course. So let's try to analyze the situation of the two torus. So the torus T2 is just the quotient of R2 modulo Z2. The first fact is that the group of all diffeomorphisms of the two torus respecting the area is not perfect, meaning it is not true, unlike in theorem of Mather, Smale, and Thurston, it is not true that any single area-preserving diffeomorphism of the circle is a product of commutators. And to see that, one has to use the so-called Khalaby homomorphism. It is a very simple construction. Suppose you have some diffeomorphism of the torus, isotopic to the identity, preserving the area. Call it F. Connect it to the identity by some path. So you have some isotopy F sub t, F0 is the identity, and F1 is the given diffeo F. Then lift this isotopy to the universal cover R2. What you get is an isotopy, capital F sub t, connecting the identity, F0 is the identity, to some F1, which is a lift of F. And then what you do is that you take the average value of the motion of F. So you compute F1 xy minus xy. So this is the vector in R2, which tells you in which direction the point has been moved. And you take the average value over this fundamental domain of this quantity. And this way you get a number, which is called a Khalaby invariant of F. And this number, C of F, has the property that it defines an actual, not quasi-homomorphism, but a homomorphism from this group to R2. In particular, if you take an element in this group whose Khalaby invariant is not 0, then this element cannot be written as a product of commutators, because any homomorphism has to vanish on commutators. However, there is a theorem due to Banyaga, which tells you that this Khalaby invariant is the only obstruction to do it. In other words, the theorem of Banyaga tells you that any element in the kernel of this Khalaby invariant can be written as a product of commutators. So this is has been proven in the 80s or something. Maybe not, 75 or I don't know. Okay, so what I want to tell you today is that commutator length is not bounded in this case. So here's the theorem. So this is a theorem that I might attribute to Ruel, even though he was not thinking this way, and that I got with Barge a few years ago. It tells you that the commutator length is unbounded inside the kernel of Khalaby invariant. So it is possible to construct area-preserving diffeomorphisms of the circle, of the torus, whose Khalaby invariant is 0, but which cannot be written as a product of a small number of commutators. So I will describe for you the construction of this invariant. And of course, the way we are doing is by constructing an explicit quasi-homomorphism from that group to the real numbers. And this quasi-homomorphism explains the unboundedness of the number of commutators. And produces a nice dynamical system invariant for diffeomorphisms of the torus. So let me explain the construction of Ruel. The construction of Ruel is very easy. You can consider a diffeomorphism of the two torus, isotopic to the identity and respecting the area. You connect it to the identity by some isotopy. So F0 is the identity and F1 is F. Now you choose some tangent vector at some point in the torus, this tangent vector. And you follow this vector by the differential of the isotopy. So you move this vector along the torus using differential of ft. And you get in this way a curve of tangent vectors in the torus. Since we are on the torus, the tangent bundle is trivial. So it makes sense to compute angles between two vectors which are not at the same point, because the tangent bundle is trivial, so you can take them back to the original point. So it does make sense to compute the angle between the original vector, let's say ddx, and its image by the differential of the flow. So you compute the angle of rotation of the differential by the isotopy. You get in this way a number. This number depends on what? Well, it depends on the original point, okay? And it depends also on the choice of the original vector. But if you change the original vector by some other vector, the number that you will compute will not be the same, but they will differ by at most 2 pi. Because if a vector gives a certain number of turns, if you move the vector by some angle theta, then the other vector will move by at most 2 pi more. So it means that if you define a first invariant, let me call little Ruel of f, as being the average value over the torus of this angle, well, this is not quite defined because this quantity in the integral is defined up to 2 pi. So this number is not well defined. It's a number up to 2 pi. If you want an actual number, you compute this. Take the limit of 1 over n Ruel of f to the n. Since this quantity Ruel, small Ruel, is defined up to 2 pi, when you go to the limit, it is well defined. And if you do that, you get an actual number, Ruel of f, with capital R now, and this is indeed an invariant of the dynamical systems. It is a quasi-homomorphism. It is non-trivial quasi-homomorphism, and actually I proved with Gambaudeau that this is a topological invariant, meaning that if two diffeomorphisms are conjugate by some homeomorphism, then they have the same Ruel invariant. So what we get in this way is that the commutator length is not bounded, but moreover, we have for free a new interesting dynamical system invariant, which I like to call the elliptic Lyapunov exponent, because instead of telling you the way vectors are stretched, it tells you the rotation of vectors, the velocity of rotations of vectors. When you iterate dynamical systems, things are rotating, and you compute the average velocity of rotation. So let's try to do similar things for different surfaces. You know that I used strongly the fact that we are on the two torus, because I used the fact that it's possible to measure the angle between two vectors at different points on the torus. Yes?
In the definition, if you take away the angle between 0 and 2 pi, then Ruel of anything is something between 0
No. Well, of course, I have to go very fast. It does not depend on the isotopy, because the group is contractible. The connect.
Translation by 0, can you move from translation by 0?
Not the kernel of Khalaby invariant.
So the identity, there is an isotopy connecting the identity to the translation by
I should say FT, you're right. I should say F belongs to the kernel of Khalaby, and FT belongs to kernel of Khalaby.
In the ending and the identity of that.
Not on the torus.
Yes, if you have translation by one on the torus, it's the identity as a group.
Yes.
As a,
Yes.
But the isotopy is a non-trivial at all. It's a translation with
Yes.
translation by zero, translation by one.
Yes. So what?
For this, the Khalaby parent is one. Is translation by is not zero.
I don't understand.
You
Oh,
lift
yes.
It's just a translation by non-trivial vector in R2.
Yes.
Integer vector.
Yes. So what?
It is the identity of the torus.
Mm-hmm. So I don't understand your point.
The point is that the definition of the Khalaby parent depends on the identity.
Yeah, but not the kernel. Not the kernel.
It's a
The
map to R2 or
R2 mod Z2, and the kernel is well defined. Okay. I understand that maybe I said something not clear, but it is clear in my mind, but not now. I extend that to you. I'm sure. And concerning your question, okay, this is maybe the yeah. Okay, so in higher genus, the situation is more complicated because you also have this Khalaby invariant, which goes from diffeomorphisms isotopic to the identity and respecting the area. And this is a homomorphism now, which is not with values in R2, but in R2G, where G is the genus of the surface. Okay, and then you have this kernel, which is again which is usually called the group of Hamiltonian diffeos of the surface. And again, we have this theorem of Banyaga that any diffeomorphism, Hamiltonian diffeomorphism of the surface, of higher G the surface, can be written as a product of commutators. And again, but this is more difficult now, and I'm going to explain to you in a moment how to do. Again, it is possible to define a quasi-homomorphism from this kernel to R. And you see the difficulty now is that if you start with a vector, as we did at the beginning, and if you move this vector by the isotopy, you do not really know how to measure angles because there are plenty of vectors at different points on the surface, and you don't really know what's the meaning of the angle between this vector, for example, and this vector. However, you can play the following game. Lift everything to universal cover. In higher genus, one knows that the universal cover of the surface of genus G is the hyperbolic disk with the hyperbolic metric. So when you lift this curve on the surface, it is a curve of vectors. When you lift it to universal cover, you get a curve of vectors on the Poincare disk. And what you can do is that each vector on the Poincare disk, you can map it to infinity using the geodesics. In this way, you get on the boundary of the disk, you get a curve. And this curve might rotate and give a certain number of turns. The number of turns is well defined, again up to 2 pi. It's not really a well-defined number, but it's a number defined up to 1. If you have a curve, which is non-closed curve on the circle, you can say, well, it turned 7 times. It's not quite true if the surface is the curve is not closed, but it's defined up to 1. So again, you can do this. You define the number as being the number of turns at infinity of this curve. This is a number which is defined up to 1. Then you average it on the surface. You get a number which is defined up to 1 again. And if you want to make a precise definition, well, you take the limit of 1 over n phi of f to the n, and this non-definition up to 1 for each single element disappears in the limit, and you get again a very nice quasi-homomorphism, which is defined on the group of Hamiltonian diffeomorphisms. And again, it is a topological invariant with a strong dynamical meaning. So again, the commutator length is not bounded. But let me go to the last case, which I like that I like most. Let's go to the two-sphere. So what's happening in the case of the two-sphere? In this case, there is no homology, no Khalaby invariant, nothing. And indeed, there is a theorem of Banyaga, again, that every area preserving diffeomorphism of the two-sphere can be written as a product of commutators. And the question is how many? And I want to present today a construction which shows that there is a non-trivial quasi-homomorphism on this group, and in particular, the commutator length is not bounded. So this is due to Gambodo and myself, and to Anton and Polterovich. Actually, I received a preprint from them last week. I had no time to understand it yet. It's using very complicated quantum cohomology and different high technology. I have no idea. Maybe I can tell you next week or something, but I have no idea how the construction works. But let me explain to you our very elementary constructions in the case of the two-sphere. Here's the trick. The two-sphere is well known to be the Riemann sphere. That is, you can compactify it. You can think of it as being the compactification of the complex numbers. C union infinity is the complex number, is the Riemann sphere, and it is well known that the fundamental invariant of 4 points in the Riemann sphere, 4 distinct points in the Riemann sphere, is the so-called cross ratio. If you give me 4 points in the Riemann sphere, Z1, Z2, Z3, Z4, you define cross ratio of Z1, Z2, Z3, Z4 as being this number. This number is built in such a way that it does not take the value 0, 1, and infinity, since the 4 points are distinct. So it gives you a number, complex number, which belongs to C minus 0, 1. And here I drew the picture of the Riemann sphere on which have put 3 special points, the point 0, the point 1, and the point infinity. So let's try to understand the dynamics of a diffeomorphism of the sphere, which is area preserving. Again, you take your diffeomorphism of the sphere, which is area preserving. You connect it to the identity by some isotopy, Ft. F0 is the identity, F1 is F. You choose 4 points on the sphere, Z1, Z3, Z4, and you look along the isotopy how these 4 points move. So you get a collection of 4 points which are moving on the sphere. At the beginning, they are distinct, and all along the isotopy, they remain distinct. So what we would like to do is to compute the evolution of the cross ratio along the isotopy. These 4 points move. At each moment, you can compute the cross ratio. In this way, you get a curve. T goes to cross ratio at time t. And you get a very complicated curve in C minus 0, 1. So here's the picture. The green sphere is the Riemann sphere. Have put 3 points, 0, 1, infinity, and the red curve is the evolution of the cross ratio along the isotopy. So the 4 points are moving on the sphere, and during this motion, the cross ratio is moving. It might be very complicated terms, and so on. So what you do is this. Imagine you are on this sphere, and you travel on the sphere. You might be in the northern hemisphere or the southern hemisphere. From time to time, you cross the equator. And then you have some walk, and you cross again the equator. And then again, you cross the equator. But you have 3 possibilities for crossing the equator. It could be between 0 and 1, between 1 and infinity, between 0 and infinity. So if you imagine that you are moving on the sphere, you have two possibilities at each motion. You can exit the equator from the right or from the left, seen from the point where you come from. Let me say that again. Imagine you enter the equator by some interval. You enter the equator. Then after, when you leave the equator, you might leave by the segment on the right or the segment on the left. Is that okay? What? All the same. Suppose I make things simple in order to forget this back and forth. So suppose I move, I don't want to get into these details, which are exactly the same questions that you ask for simplification in the case of Brooks co-cycle, okay? So imagine you don't have back and forth. So you move, and if you move in, you can go on the left or on the right. Sorry, on the right or on the left. Then you count how many times you go to the left minus how many times you go to the right. This gives you a number which measures kind of the complexity of this red curve. This is an integer. And I think you can guess the end now. Well, you take the average value. Take the average value of this number of turns. But now it's an average over the set of all four tuples. You have to average this quantity over all possibilities of all four tuples of points. It tells you it's a measure of the complexity of the motion, kind of a vorticity of the fluid motion, I would say. And again, if you want to make it this well-defined, you have to go to infinity, limit 1 over n, phi of f to the n, and this gives you a number which is well-defined, which is a quasi-homomorphism, and therefore which gives you lower bound for commutator length. And again, one can show that this is invariant under topological conjugacy, and therefore is an invariant of the dynamical system. So this gives, I think, an elementary construction. I have to check whether or not this invariant is the same as the invariant introduced last week by Polterovich and Entov. Probably yes, I have no idea. But at least this is a very simple idea. In order to finish, let me take as a conclusion the fact that one can be a little bit more sophisticated, and instead of using 4 points, one could try to use more points, n points. And instead of looking at the motion of 4 points on the sphere, you could take a dozen of points or n points. And when they move on the sphere, instead of creating just a cross ratio, they create a braid, which is a topological object that people from topology like. And braids have a lot of invariants, in particular symplectic invariants. One can use, instead of taking the homotopy and the cross ratio, one uses the Maslov class, and Maslov class gives you another collection, a huge collection of examples of quasi-homomorphisms, and therefore a huge collection of topological invariants for the dynamics of diffeomorphisms of the sphere. So in this way, you get many, many possibilities of construction of topological invariants, and as one might even dream that these invariants are sufficient to distinguish between conjugacy classes, but that's another topic. So let me give the conclusion of this talk. Conclusion is this: I believe that it might be a good idea to look at quasi-homomorphisms systematically. And systematically, this might create and produce interesting dynamical system invariants. For example, I showed you that on surfaces, but I must say that if one takes the diffeomorphisms of a surface which are not respecting area, I have no idea of how to construct similar objects. And in particular, if in the higher dimension, like 3 or more, I have no idea whether or not the commutator length is bounded or unbounded. I would guess it is unbounded. I have no proof for that. But in any way, in any case, if one wants to show that the commutator length is not bounded, one should try to have geometric ideas to construct quasi-homomorphisms, and that could be useful for dynamical systems. Thank you very much.
questions?
Yeah, quasi-homomorphism gives you a linear bound from
Yes,
the length,
yes,
from the power.
yes.
Is there some, I mean, there is something
Yes, it is.
bounded and linear bound?
Yeah, in some groups, for example, the commutator length of gamma to the n might be square root of n. In some, for example, the Heisenberg group is a typical example. So that's an interesting question, but I would say question of second order. This is the first thing to do. Then one might ask, what about the sublinear growth for commutator length? But this have no tool to study it.
More questions? Okay, then thank you very much.
No, come.